This is chapter 25, part 2, Reflection and Refraction. And in this lesson, we're going to learn about these two phenomena of light that are very common, and we experience them every day. Refraction is the phenomenon of light that's behind the rainbow. We see a little bit of that here with white light entering a prism, and then it's separating out into its constituent colors. We're going to learn why that happens. We'll also learn about real rainbows. And of course, we'll learn about reflection, which we always see when we look at the surfaces of water or at mirrors. And so this lesson will be the foundation of optics.
All right, so let's talk about colors. White light contains all colors, and we can see that in the prism image from the previous slide. The white spreads out into all the colors. So even though we often think of white as the absence of color, it's actually all the colors together. Don't think of it as mixing a bunch of paint, because if you mixed all the different paints together, you would just get kind of a brownish black sludge. No, that's not what we're talking about here. We're talking about different colors of light combining, and all combining to make white. Now, white objects reflect all colors. Certainly white objects absorb a little bit of light, but they reflect most of it, and they reflect colors from the whole spectrum. Now, black objects absorb all colors. That's why we see them as black. They don't reflect a certain color, and in fact they do reflect a little bit, otherwise we would not see them. They would be invisible. We clearly know from experience that black objects are not invisible. But we see them as black because they absorb most of the colors or most of the light that hits them. And they absorb wavelengths, all the different colors in the visible spectrum, all the different wavelengths that make up the colors of the rainbow. Black objects absorb them. This, by the way, is why black objects get hotter out in light, especially sunlight, than white objects do, because they absorb more light, which means they absorb more heat. Or rather, the light they absorb results in their heat, which they then radiate as infrared. All right, so green objects absorb all colors but reflect green. And so that makes sense. If you think of a green leaf, or I don't know, a greenhouse, or any green thing that you can think of, a green frog, if you want to think about it this way, they're actually everything but green, because they absorb everything but green. We see them as green because that's the main color that they reflect. Now, that doesn't mean it's the only color they reflect, but it's the main one that they reflect. Now, red, green, and blue light can be combined to produce any color. Keep in mind that as I'm talking now, again, don't confuse this with what you learned perhaps in grade school when you were learning about color mixing. You might have learned about mixing paints or pigments, markers, or any different type of thing that we use to color paper. But those rules are completely different from the color mixing of light. So when we're talking about producing colored light, we always combine red, green, and blue. Now, you might remember some of the old TVs actually had a red light, a green light, and a blue light in front of them that would project onto a screen. And then actually all computer monitors today, color computer monitors, they use combinations of red, green, and blue. In most cases, they use 256 different shades of red, 256 different shades of green, 256 different shades of blue. And if you multiply 256 by itself, right, or you cube it, that will give you all the different colors that you can produce on a computer monitor. So red, green, and blue light then are combined in these ways. This is called additive color mixing. Additive color mixing refers to getting colors from light. So the primary additive colors are red, green, and blue. And then they combine to form yellow, cyan, magenta, and in the middle, white. Now, let's try to understand a little bit why red and green make yellow, or why red and blue make magenta. And I think the best way to understand that is by looking again at the visible spectrum. And we see that the higher wavelength, lower frequency light, that's on the red end, and then the lower wavelength, higher frequency light is on the blue end. Well, let's kind of break it up into left side, middle side, and right side. You can see if you look at the middle that that's green. So middle is green, left is red, right is blue. And these are really the three areas, the main areas of the spectrum that we're talking about. So how do red and green combine to make yellow? Well, think of it this way: they kind of meet in the middle. So red light and green light meet, and since they're one on top of the other, that superimposition of two different colors produces the color that's in the middle, and that's yellow. Or think of it this way: if you've got green in the middle and you've got blue on the right, well, what do blue and green produce but what is in between them? And what's in between them is cyan. What's in between them is cyan. And finally, this one you kind of have to use your imagination for. You kind of have to wrap this purple side over to the red side and then just kind of imagine what that blend would be. And you can pretty clearly imagine it to be a bluish red or a magenta. And then if we have all the colors together, well, then there is no meeting in the middle. It's just putting all the colors together. And then what you'll get is you'll get white. All of those frequencies superimpose on each other to get the combined effect of pure white light. All right, so this is kind of a goofy animation, but it's going to show you what color the guy's thinking when different colors of light hit his eyes. Now, what he's thinking at this moment is black, because no color is hitting his eyes, and black is the total absence of color. All right, so if we give him a lot of red, suddenly his eyes are showered with red photons, and he sees the color red. All right, let's give him the color green. Well, suddenly eyes showered with green photons, he sees green, and of course you can predict what blue will do. All right, so those are the three primary additive colors. Now let's look at the combinations. All right, if we give him some red and we give him some green, well, he'll see what meets in the middle, and that's yellow. All right, let's give him some green with some blue, and what meets in the middle? Well, cyan. And now let's give him some blue and some red, and what does he see? They blend together to make magenta. All right, now let's give him everything all together, and he sees pure white light. Pure white light. Now, if we do different combinations, and this is exactly how computers make the colors that you see on the screen, is different combinations of red, green, and blue. So say we decrease red a little bit, and let's say we decrease blue a little bit. Well, now what is he seeing? He's seeing kind of a, I don't know, it looks like kind of a weird green. If we give him less green, well, now what he's seeing is kind of, I don't know how to describe it, almost a lavender, or I don't know, a brownish purple. It's hard to describe that color. Let's give a little more red, and now we see something that looks, I don't know, like a fuchsia or something. And then let's give a little more blue, and now what we're seeing is a light purple. And the point is that all the colors that we see on a computer screen are just made from different combinations of red, green, and blue. Now, that was additive color mixing, and I'm going to show you. A demo of additive color mixing in class with actual light in a dark room. But now let's talk a little bit about subtractive color mixing. So cyan, magenta, yellow, and black pigments can be combined to reflect any color. Notice that the three secondary additive colors are the three primary subtractive colors. And let's take a look at what they make. Well, if you mix cyan and magenta, you get blue. If you mix cyan and yellow, you get green. If you mix magenta and yellow, you get red. And so then the secondary subtractive colors are the primary additive colors. It's kind of interesting. Now, why is there black? Well, black is not really, you can't really call it one of the primary subtractive colors. But when you do four-color printing, like if you get a brochure printed, any type of color printing, you've probably seen this if you've replaced the ink cartridges in a printer. There's the C cartridge, the M, the Y, the K. Well, it's easier to make black with black ink than to waste a lot of cyan, magenta, and yellow and put them all together at a high intensity to get black. So it's actually more efficient to use some black ink in addition to cyan, magenta, and yellow. Now let's talk a little bit about how subtractive color mixing works, because it's not that intuitive. But if we look at these images here, what we see is blue paint. Blue paint absorbs a lot of different frequencies of light, but it reflects blue and green. Now, it reflects blue more strongly than it reflects green, and different hues of blue can have different ratios of blue to green that get reflected. But still, it's reflecting blue and green. Now, how about yellow paint? Yellow paint is absorbing most, but it's reflecting yellow and green. Certainly reflecting more yellow than green, but still reflecting both. Now, if we put blue paint together with yellow paint, and this might be more familiar to you from grade school, well, we'll get green, but here's why we get green. It's because now everything's getting absorbed. Everything that blue absorbed, plus everything that yellow absorbed, all of those are getting absorbed by the green paint. And the one thing that's getting reflected is green. So this is how subtractive color mixing works. And of course, it's the easiest to see is blue, yellow, and green here. But you know, this applies more directly to cyan, magenta, and yellow. You can think of, if you like, think of cyan as your blue paint, and think of magenta as your red paint, and think of yellow as your yellow paint, because you probably also learned in grade school that the primary colors were blue, yellow, and red. Well, actually, that's true, but it's more accurate to say that the primary colors for pigments are cyan, magenta, and yellow. So an interesting question is, why is the sky blue? And a related question, why are clouds white? Well, the sky is blue because of something called scattering. And so here's how scattering works. You already know that when light passes through something transparent, such as air, what it does is it gets absorbed by atoms in the medium and then re-emitted. So absorbed and re-emitted, absorbed and re-emitted. Now, when air molecules such as oxygen and nitrogen, which are tiny little molecules, when they when they absorb light, they get excited to a high frequency because they're small, and the light that they re-emit is also at a high frequency. So you could think of it this way, or another way I think that's maybe better to think about it is that um, white light from the sun contains all frequencies, but the higher energy frequencies of blue are they're going to be re-emitted from an atom that moves back and forth at a high speed. And so if you have an oxygen molecule and that gets excited, well, what that means is its electrons go to a higher orbital or a higher energy state, and then when those electrons come back to their ground state, they release energy in the form of a photon. Well, what those small, easily excitable molecules will do is release a high energy photon. Think of it this way: if you have small jingle bells and you shake them, they're going to make a high pitched sound. If you have a big old, I don't know, prayer gong or something like the Liberty Bell and you hit that, it's going to make a bong, bong, low sound, right? Well, the same applies to molecules. If you excite a small molecule and get it to re-emit photons, those photons will be high frequency, such as the blue. If you get a large molecule and get it to re-emit photons, those are more likely to be in the red wavelengths. All right, so the reason we're seeing blue is we're seeing the photons that have been absorbed and re-emitted by tiny air molecules, and it's called scattering because it gets sent in all directions, not in just one direction, but these molecules are moving all over the place in all kinds of different orientations, millions of times per second. And so what that means is we're going to have this kind of diffuse and widespread light that's going in all kinds of directions. And of course, some of that light just gets reabsorbed and re-emitted again as blue. So we can get different kinds of blue depending on where in the horizon you're looking, how bright the sun is, what the air quality is. So that's why the sky is blue. It's because of the scattering of light by small air molecules that re-emit the photons of a high frequency precisely because they are excited to a high frequency by the light that hits them. Now, why are clouds white? Clouds are white for a similar reason, but the color is different because clouds are made up of many different sizes of droplets. Some of the droplets are tiny, maybe only a couple of molecules of water, and some of the droplets can be quite large, hundreds, thousands of molecules of water. But you have a mix of all these different sizes in a cloud. And so what you'll get then is you'll get the absorption and re-emission of all the different frequencies of light. The bigger molecules will absorb and re-emit on the red end. The medium molecules will absorb and re-emit kind of in the middle yellow portion. And then you're going to get the small molecules absorbing and re-emitting in the blue portion. And since you have all these different sizes and all these different frequencies, the result is white light, which is the synthesis of all colors. Why are sunrises and sunsets red and orange? Well, it helps to think of the path that the sun makes through our atmosphere on its way to the surface of the planet. All right, so let's think of it this way. So let's take a look at why the sunlight is red at sunset. Right, if you look at this image here, we see a picture of the Earth, and then we see the sun at noon, and the sun at sunset. Now notice when the sun's up here at noon, an observer on the surface of the Earth, let's say the observer is right at this spot. I'm going to mark that spot with a little red circle. So let's say the observer is right there. If that observer looks up, he's going to see a blue sky because this is a short path and the blue light is getting scattered by those small air molecules, as we talked about a little bit earlier. Alright, so if he looks up, he's going to see a blue sky. Now, how about later on in the day when he sees the sun setting? Over here, the sun's setting in the west. The same observer in the same place is looking at the sun. Notice that there's a much longer path. Also notice that besides the fact that the path is long, that sunlight has also traveled through more of Earth's atmosphere on its way to the observer at sunset than it has on its way to the observer at noon. Okay, we can see that here. What I'm tracing right now is a pretty short path through Earth's atmosphere, and then what I'm tracing right now is a fairly long path through Earth's atmosphere. Now, why the difference in color? The reason is that as sunlight passes through the atmosphere, more and more of its blue light gets scattered out. Okay, so let's go back to this short path right here. This short path is not long enough to scatter out all the blue, and that's why someone looking up is going to see a blue sky. But this path over here, now watch the pencil, this path over here is long enough so that by the time the light reaches the observer's eyes, most of the blue light has been scattered out by the atmosphere, leaving only the red and orange and yellow end of the spectrum remaining. And that's why we see these brilliant oranges and reds and yellows at sunset, because the blue has been scattered out. Another question is, why is the ocean blue-green? And if you just have a glass of water or even a glass of salt water, you're not going to see any blue color. It's just going to be transparent. But if you dive down a few feet, whether it's a pool or the ocean or a lake, if you dive down, you're going to see that the water gets progressively bluer. In fact, it's kind of a blue-green. Well, here's the reason, and we're going to really quickly go back to the visible spectrum. Okay, notice how red is got a high wavelength, low frequency, and that means it's the lower energy visible light, whereas blue and violet are the higher ones. Well, do you remember what was immediately before red? And I'll draw it small here just for the sake of room. You might remember that immediately before red is what we call infrared. So I'll mark that here just as IR. Now, of course, the band is a lot wider than that, but I just want you to remember what the positions are. And then before infrared, we had another fairly wide band, and that was microwaves. So I'm going to call those MW. So we have MW, IR, and red. Well, it turns out that in this region, and so I'm circling kind of the right-hand side of microwave, all of IR, and a significant portion of red. In that whole region I just circled, it turns out that water molecules do resonate with those frequencies. Now, the effect is much more pronounced, of course, with the higher end of the microwaves, because the water molecules resonate fast enough to heat water, to heat food. But the IR and red interactions with light are significant, because what we have there is we have red light and water molecules causing a little bit of resonance, and also infrared will cause a bit of resonance with water. Certainly, not quite as much as the microwaves, but enough, for example, for sunlight to easily heat water. And because the water molecules, like in a pool or at a lake, are resonating slightly with the infrared wavelengths. And this also happens with the red portion. And so, since the red portion of light tends to make the water molecules resonate slightly, that really amounts to an absorption by the water of the red wavelengths. So what does that mean? That means as you go deeper and deeper, all you're left with is really this portion of the visible spectrum. And that's because the red and even the wavelengths that are kind of to the right of red have been absorbed out. And so you're left with the bluish green portion of the spectrum. And that's why when you get to the bottom of a lake or the bottom of a pool, or you get fairly deep, still with visibility, but fairly deep in the ocean, you're going to see it blue-green. And that's because the red has gone missing. All right, so we talked about colors, and we're now ready to move on to a new topic, which is the reflection of light. The law of reflection states that the angle of incidence equals the angle of reflection. So we're used to reflection. Every time we look in a mirror, we have the law of reflection at work. And the angle of incidence is this angle here. The normal, by the way, is a vertical line that is made with the plane of the reflective surface. And that normal then, of course, is perpendicular here, and then theta I is the angle of incidence. Theta R is the angle of reflection, and theta I equals theta R. So let's suppose, for example, that you had, I don't know, an incident wave coming down like this. Well, what would the bounce look like? The bounce would look like that. Okay. Obviously, these are terrible lines. I'm just making them with a mouse, but you get the picture. If you have a big theta I, you'll have a big theta R. If you have a small theta I, you'll have a small theta R. Reflection from a smooth surface is called specular reflection. If the surface is rough, it is diffuse reflection. So specular reflection is the kind that we see in mirrors, because mirrors are highly polished and smooth. But diffuse reflection is what we see like on a whiteboard in the classroom. The whiteboard reflects light, reflects all the colors, that's why we see it as white, and it looks fairly shiny. But you can't really see a reflection in it. I mean, you can a little bit, but certainly not as well as you can in a mirror. And that's because the surface of the whiteboard is rough like this. And it's definitely not smooth and polished. So you won't see yourself very clearly in the whiteboard. Now, water can sometimes approach specular reflection. Here we have a beautiful image of a lake reflecting the trees and the mountain, and what we have is not specular, but you can see that the water is fairly calm. There's not a lot of wind to turn up the surface, and therefore we have a pretty nice reflection. Now, if there were no water current whatsoever, if the water were completely still with absolutely no breeze, you would get perfect specular reflection here. But those conditions, of course, are very rare. Forming images with a plane mirror. So light reflected from the flower and vase reflects off the mirror to the eye. The eye interprets the ray as having had a straight line path and sees the image behind the mirror. So these dotted lines here are what we would call virtual rays. And our eyes interpret those as straight lines. Our eyes don't interpret this as lines or rays that bounced off something coming to our eyes. I mean, we know that's what's happening. But what we see is we see an image actually behind the mirror. And we see it reversed reversed left to right, although not top to bottom, because what we're seeing is we're actually seeing something in the mirror. By the way, quick little clarification: why, or sometimes questions asked, well, why do we see things flipped left to right but not up, top to bottom? Well, imagine you're looking at yourself in a mirror, and you put your hands to the mirror. Well, if you put your left hand to the mirror, notice that that left hand of yours is the right hand of the mirror image. And if you put your right hand to the mirror, notice that that right hand of yours is the left hand of the mirror image. All right, so things, obviously, you just take a moment to reflect on that, no pun intended. If you take a moment to reflect on that, you'll see that it's true, that left and right switches, but your top, so that your forehead is going to be the forehead of the mirror image, and your feet will be the feet of the mirror image. There's no top bottom flipping. So the properties of mirror images produced by plane mirrors are these. A mirror image is upright but appears reversed right to left. I don't know if you ever noticed that the word ambulance is written backwards on ambulances, so that when you see them in your rear view mirror, when you see that word in your rear view mirror, it's going the right way. It's readable. A mirror image appears to be the same distance behind the mirror that the object is in front of the mirror. So if I'm 5 feet from a mirror and I look at my mirror image, it looks like my mirror image is 5 feet into the mirror, as if I were standing behind it. And certainly if you showed a mirror to a baby that's never seen a mirror before, the baby will simply understand that his image is behind that mirror. Okay, the baby doesn't know what a mirror is, and so to the baby it just looks like he or she is right behind that mirror. A mirror image is the same size as the object. Okay, that makes sense. We're not going to see it as smaller or bigger if it's just a flat mirror. Now let's talk about the refraction of light. So the refraction of light is the bending of light, and light bends because it travels at different speeds through different mediums. I guess you would say through different media. But in any case, it travels at different speeds through whatever it's traveling through. Now, if it's traveling through air, it's going faster than if it's traveling through glass. And if it's traveling through water, it's a certain speed. It's actually a little bit faster through water than it is through glass. And so the refraction is different. We can see that a little bit here. We can see that it's almost like there are 3 different portions of this image, and that's because we're looking at it through 3 different media or combinations thereof. Here we're just looking through the air. Here we're looking through air and glass, and here at the bottom we're looking through air, water, and glass. All right, so the refraction of light is the bending of light. And now let's learn why light bends. A simple analogy for understanding refraction is this truck. Now the truck is on a smooth surface above, but the purple is carpet, and the carpet is rough. And so it's naturally going to go faster on the smooth surface and slower on the rough surface. Well, what happens is if the car reaches the carpet at an angle, the first tire slows down while the other tire is going fast. And so the tendency then is for the whole thing to turn. And then the back tire hits the slow surface and turns more. So let's look at that again. It turns precisely because it hits at an angle, and part of it, the part of the truck that hits the carpet first, goes slower, and the rest goes faster until the whole thing catches up, but by that time it's turned. Now let's take a look at this little drawing. Okay, so we're going to draw the normal, and the normal is perpendicular to the boundary between the 2 mediums or media, and then we have the angle of incidence, and of course when the beam comes out we have the angle of refraction, or theta 2, and notice that both angles are in reference to the normal. Now, let's suppose we have the fast surface or fast medium up top and the slow surface or slow medium on the bottom. Well, let's take a look at how that refraction is going to look. All right, so what we'll do is we'll look at the truck and say, well, if the truck starts out in the slow medium, so now there's the opposite situation, how is it going to turn when it enters the fast medium? Well, what happens is it'll turn the other way. Instead of turning toward the normal, it'll turn away from the normal. And it's for a similar reason. It's because now the first tire that enters the fast surface and will tend to speed up while the other tires are still in the slow surface. So let's take a look at that again. Notice it bends away from the normal when it's going from the slow medium to the fast medium. Now let's take a look at another analogy that can help us to understand refraction. And let's pretend we've got a marching band, or if you like, a bunch of soldiers marching people. Okay, and we've got marching people who are going through a road through which they can march faster. They're going at an angle, and then suddenly there's a boundary between the road and a swamp through which they're going to march a lot slower. Well, let's look at what happens to this line of people. Well, the first one to hit the swamp slows down. And then what you have is you have subsequent people hitting the swamp, and the overall effect you're going to get is a turning. Okay, so if we draw the rows of marchers this way, notice that once they hit the swamp, there is a turning precisely because those marchers have now encountered a slower medium to march through. Okay, and so you'll get kind of a bunching up of the first marchers that enter the swamp. And the overall effect, after everyone adjusts, is for a change in direction of the march. And so if we were to draw that lined up, it would look like this. You can see clearly how the direction has changed. Well, this is very similar to how light really works, because light travels in wave fronts. And so, you know that if you have a beam that goes in, well, that beam has a thickness that we can't see because it's made of photons. But those photons travel in waves. And so just like ocean waves have wave fronts, or a line along which the wave is breaking, well, the same is true with waves of light. And so the wave then will have an angle of incidence and an angle of refraction. And those angles are made, of course, with the normal. And so the analogy of marchers, whether they're soldiers or marching band, going from a road to a swamp is helpful for understanding why light bends. Because light bends for a similar reason. The first photons that hit the slow surface or the slow medium are bent, and then the rest catch up so that the whole beam bends. All right, so let's look at this prism here, and let's say we direct a laser to it. Well, we can see that the light is refracting through the laser. All right, refracting through the prism. So that laser is refracting through the prism. We can see that the laser enters the prism and then exits after it bends, and we can trace its path through the prism. Okay, so it enters, some of it reflects, but some of it enters the prism. And if you look closely, you can see that there's a line, a distinct line. So that's the entry point right here, marked. And then this is the exit point. And so if we mark the entry point and the exit point, and the point from which the light originated, we can trace out that laser beam and its resulting path through the prism. And that was the path through the prism. Notice that it enters, it bends towards the normal because it has entered a slow medium, and then when it leaves the prism, it now bends away from the normal again. All right, so now that we've learned why light bends, let's talk a little bit about the math behind it. Now, this derivation that I'm going to show you, you don't have to know for the test, but I think it's important to show how all these quantities are related. All right, so let's first look at the most important two rays in the diagram. And that is this purple ray right here and the purple ray down here. We can think of the green area as a fast medium, and the brown area as a slow medium. If you like, I guess we could call this up here air. So let's say that air is our green area, or our fast medium in this particular case. And then down here we can say that this is could say it's water. Okay, so the brown area is water. Now we know that the light is going to go faster through the air than it will through the water. And because of that, the light will bend towards the normal when it enters the slower medium. So light's marching along fast, 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 and then suddenly it encounters some slow medium, and then it bends appropriately towards the normal. Kind of like in the same way that we just went over on the previous slide. All right, well, if light has a faster velocity in air than it has in water, well, then certainly V1 is bigger than V2. And for a given small delta t, V1 delta t will be bigger than V2 delta t, precisely because V1 is bigger than V2. All right, well, now let's look at some similar triangles. Theta 1 is my angle of incidence. Theta 2 is my angle of refraction. First similar triangle to look at is this guy here, and I'm tracing it right now. I'll trace it again. Okay, so that's the first triangle to look at. Let's see where we get it from. All right, well, if this is 90 degrees, then up here we also have 90 degrees. And that means that this angle here is the complement of theta 1, which means 90 degrees minus theta 1. Well, if this is 90 degrees minus theta 1, then of course this angle over here must be theta 1. All right, that's one similar triangle. Now let's look at another similar triangle. So this little triangle down here is defined by the purple ray and then a green line that is parallel to this green line up here. Theta 2 is the angle of refraction. If this is 90, then so is this. And if this is 90 here, then this angle is the complement of theta 2, 90 degrees minus theta 2. If this is 90 degrees minus theta 2, well, we know from alternate interior angles of parallel lines that this angle here must be 90 degrees minus theta 2. In which case, since this is perpendicular, and I'll draw a big perpendicular here so you can see that. In which case, if you have 90 minus 90 minus theta, so 90 minus 90 minus theta, all that's going to give you is theta. And so theta 2 then must be this angle. Now we'll talk about this triangle here, the big one. If I know this is theta 2, okay, and this is V2 delta t, I can set up some trig equations. So let's start with sine theta 1 equals V1 delta t over hypotenuse. All right, why is this true? Well, V1 delta t is this distance here. And so that's this portion. Okay. Sine is opposite over hypotenuse, so sine of theta 1 is opposite, which is V1 delta t, over hypotenuse, which is this line right here. All right, so what I'm tracing back and forth now with the mouse arrow is what I mean by the hypotenuse of that triangle up there. Okay. All right, so this triangle then, this big right triangle that I'm tracing, is such that the sine of theta 1 is V1 delta t over hypotenuse. Now let's look at the other triangle. Sine of theta 2 equals V2 delta t over hypotenuse. Well, that makes sense too, because V2 delta t is the length of the opposite side. These two triangles share a hypotenuse. And so the sine of theta 2 equals V2 delta t over hypotenuse. Now we can rewrite as V1 delta t over sine theta 1 equals V2 delta t over sine theta 2, which becomes V1 over sine theta 1 equals V2 over sine theta 2. And this makes sense. I know that V1 is big and V2 is small if we compare them to each other. I can see that theta 1 is big and theta 2 is small if we compare them to each other. And so it stands to reason, if you want to think about it this way, just looking at this equation down here, big over sine big equals small over sine small. So the equation makes some sense in that way too. Now we can finally write the angle of refraction is related to the different speeds in this way. Sine theta 1 over V1 equals sine theta 2 over V2. It's just a rewriting of what we just said. Okay, so what that will mean then is you're going to have, if you have this index, or this refraction index is high, that is, if this is a slow medium, then it's going to bend the light more than it would if it were a fast medium. And that means that the angle will be different. Okay, so bending more means that for a slow medium, theta 2 becomes quite small. For a faster medium, theta 2 is not as small. And the difference between theta 1 and theta 2 is more marked the greater the difference is between the speeds of these mediums. All right, so the main thing to remember is that the sine of theta 1 over V1 equals the sine of theta 2 over V2, which means that the angle of refraction is related to the different speeds. Now, the speed of light in a medium is given by the index of refraction of that medium. And the definition of the index of refraction. Remember, this is a definition. This is not a proof. This is just the way that something is defined. V, that is the velocity of light going through a medium, equals C, which is the velocity of light in a vacuum, divided by N, which is the index of refraction. Now, a high index means a slow medium, and a low index means a fast medium. Let's take a look at some different indices of refraction. Now, it makes sense that solids in general are going to have a high index of refraction because they're denser. Liquids will be medium, and gases will be low. The index of refraction of diamond is impressive, 2.42. All right, so let's go back here. If the N of diamond is 2.42, that means that light traveling through a diamond is C over 2.42, or 1/2 C. In fact, it's right about 1/2. It's a little less than that, because 1 over 2.42 is a little less than 1 over 2, right? Because 1 over 2.42 would tend to approach like 1/3, which is definitely less than 1/2. But in any case, it's about 1/2, and that means that that light travels half as fast in a diamond as it does through a vacuum. All right, and then we have glass, which is around 1.5 or so, water 1.3, and then carbon dioxide and air very close to 1. So close to 1, in fact, that it's hard to measure the difference. But what we see here is that the index of refraction depends on the material. And in general, the denser the material, the higher the index of refraction. All right, let's talk more about the refraction of light just to arrive at another equation. So if sine theta 1 over V1 equals sine theta 2 over V2, which we've already seen, and we keep in mind that V1 is defined as C over N1, where N1 is the refractive index of substance 1, and N2 then is the refractive index of substance 2. We have light going through two different substances here. Well, then we can rewrite, so we have N1 sine theta 1 over C equals N2 sine theta 2 over C, and that brings us to Snell's law, which is N1 sine theta 1 equals N2 sine theta 2. All right, so this then relates the refractive index to the angle of refraction. And this is convenient because if we measure angles, if we get a laser, for example, and shine it through air into a different medium and measure those angles carefully, we can actually calculate indices of refraction. Let's take a look at this example. We have air at an angle of incidence of 60 degrees, which means, of course, the angle of refraction the angle of reflection is 60 degrees. All right, so it comes in at 60, reflects at 60. Remember, some of the light gets reflected and some of the light enters the medium and gets refracted. Well, notice that the light that enters the water and gets refracted is at an angle of 40.6 degrees. That's its angle of refraction. Well, if we look at glass, which has a higher index of refraction, all right, angle of reflection is still the same, 60 degrees, which equals the angle of incidence. Nothing new there. But notice that it has a lower angle of refraction. That means that this ray has been bent closer to the normal. See, 35.3 is less than 40.6, so it's closer to the normal. All right, so let's use Snell's law to calculate the index of refraction of glass. And let's take a look at this image down here. So we know that N1 sine theta 1 equals N2 sine theta 2. N1 is the index of refraction of air, and theta 1 is this 60 degrees, which is the angle of incidence. N2 is the index of refraction of glass, and theta 2 is the theta, or the angle of refraction. Okay, so if we look at the quantities here, we can see that they fit right into Snell's law. We use 1 for N1 because air is close to a vacuum. It's certainly not a vacuum, but the index of refraction is fairly close to it. And so we're just going to use 1 for air, sine 60 degrees. And then we have N2 that we're trying to find, it's sine 35.3 degrees. And we find that N2 equals 1.5, which is, that agrees with what we would expect for glass, about 1.5. So Snell's law then relates the indices of refraction to the angles of incidence and refraction. Now, the refraction of light has some interesting consequences. One common optical illusion that we're all familiar with, if you've ever looked at your hands or your feet in a pool, or I don't know, stuck a pole into the pool, like to pull out some debris. You've seen this effect, and the effect is that the object appears to bend. Well, really what's bending is just the light, and refraction causes that apparent bending. An even more interesting phenomenon is mirages. So the way mirages work is, let's say that the light from this tree is headed downward. Now, light, of course, radiates in all directions. Okay, so if you're thinking about the light off of this tree, well, you know, light reflects in all directions, and that's just because light is hitting it from all sides, whether it's direct or indirect light. And so, like, if you go 360 degrees around this tree, you'd always see it. It would never be invisible. But what matters is, for us right now, is the fact that some of that light goes straight down this way. Now, what happens to that light? That light is directed towards the ground. But keep in mind that the ground is quite hot on a sunny day. And that means that the air above the ground is hotter than the air that's maybe 10, 15 feet above the ground. And what that means then is that you have a difference in density. So the hot air that's close to the ground is going to be less dense than the somewhat cooler air that's farther up off the ground. And that means that the refraction will be different. Okay, so light actually travels a tiny bit faster through the less dense air that's close to the ground than it does through the more dense air that's farther from the ground. And so what you get is, because there's a gradual difference in density, it's not a sudden boundary like we have up here at the top left. It's air and then a sudden boundary of water, right? That gives us straight line and angled bending. Well, this is not angled bending. This looks more like a curve. And it's a curve precisely because the index of refraction is gradually changing. It's gradually decreasing as you get closer to the ground. And so what that will do is bend the light along this curved path so that it comes to the observer's eyes. Now, remember, our brains only interpret straight lines when it comes to light rays. And so what we see is, we see that light, but we see it as coming along this dotted line is the virtual ray, as coming from the ground. And of course it's not coming from the ground at all, but that's the illusion. That's how our brain interprets the information that the optic nerve is sending to it. So we see this straight line, and so what we think it is a reflection of the tree in the ground. And the most common sense assumption is that there's water there causing the reflection. Well, this is the phenomenon of mirages. If light enters a medium of lower index of refraction, it will be bent away from the normal. If the angle of incidence is large enough, the angle of refraction is 90 degrees. At larger incident angles, the light will be totally reflected. All right, this is a pretty interesting phenomenon, and it actually can cause the invisibility of an object underwater when it's seen from a low enough angle. Here's how it works. All right, so we have theta 1 here, and theta 1, because this is the angle of incidence and this is the angle of reflection. And so we know that some light will be reflected back, and some light will enter the medium 2 and will bend away from the normal. All right, so we can think of material 1 in this diagram as water, and material 2 as air. Okay, and so since the light originates in the water and then comes out, well, it's now entering a faster medium, and so it will naturally bend away from the normal rather than towards, as it would if it were a slower medium. Okay, so theta 1 is the angle of incidence, and theta 1 is also the angle of reflection. Theta 2 is the angle of refraction. And all this theta 1 less than theta c means is that it's less than the critical angle. We're going to see in a minute what the critical angle is. Now, if we increase theta 1, we're still going to get some reflection back within the water itself and some refraction out of the water. And so an observer here, for example, let's say we had that ever-present eye of physics that you could just draw right here. Okay, so you have the eye of physics, and that's our observer, and it's looking at this. Well, if that eye sees this ray, the eye will think that it's seeing something here. Okay, so I'll just kind of do a dotted line. Well, it's actually a terrible dotted line. It's kind of hard to draw lines with the mouse here. Okay, so you can pretend that's dotted. But the eye thinks that it's seeing something over here, when actually the thing that it's seeing is right here. Okay, let's say that's an object. Well, so the eye is already thrown off even at this angle, but theta 1 is still less than the critical angle. Now, if we increase the angle, so now theta 1 is even greater, What that's going to do is we're going to reach a point at which theta 1 equals the critical angle. And the critical angle means that, that the angle of refraction is now 90 degrees. Okay, so the theta 1 that is required in a certain medium to achieve a theta 2 of 90 degrees, that's your critical angle, which means that that observer, let's say that we have that same observer over here who was looking at something that he thought was over there. Well, that observer now is not going to see anything. And he might have a big question mark, right, in his head, because suddenly he sees nothing. It's disappeared. It's disappeared. And he's not likely to put his eye down here and see the light. But if he did put his eye right on the surface, that's where he would see the object as coming from right on the surface. And then finally, if theta 1 is greater than the critical angle, then what happens is all of the light simply stays within the slower medium. All of it reflects within the slower medium, and none of it refracts out. It's almost as if the light is trapped in the water. And so if the angle, the angle here, the theta 1, is big enough, and you have an observer, and he's looking at an angle over the water, he is not going to see anything. Now, of course, if he were to change his angle of sight and look down directly into or directly above the object, he'd see it. But if he's looking at the object or trying to look at it from this angle, he's never going to see it. It will be completely invisible because none of the light from the object will refract out of the water. Let's take a look at this animation here. It's kind of interesting. And what we have is we have a laser beam, and we've got our normal line here. And we can see kind of what's happening. The laser beam starts in the air, and then the beam enters the water. Notice that the beam here enters a slower medium, and therefore it bends towards the normal. Notice also that we have always some reflected light. Now, we're not going to achieve a critical angle here because we've got the light entering from fast into slow. But when I switch that, we're gonna see a critical angle. Notice a couple interesting things here. So if I hold this kind of low, there is there's a big angle of incidence and a pretty big angle of refraction. And then if I reduce it, that decreases almost to the point where it's becoming close to equal. And then when I hold it directly above, notice that there's no refraction at all. Okay, there's no refraction at all. The light goes straight down into the water, and of course the light slows down once it's in the water, but it doesn't bend at all because the angle of incidence is 0. Okay, so remember, angles are always given in reference to the normal, and so when the angle of incidence is 0, then there's no refraction at all. All right, let's take a look. Let's now change it. We're going to go the opposite way. We're going to go from water into air. And let's see how that works. Okay, well, when we're here, okay, so we haven't reached the critical angle yet. But as I move it down a little bit more and more, I get close to the critical angle, and right there is the critical angle. Okay, I've reached the critical angle. Notice that once I go past the critical angle, the light just stays completely in the medium. This is called total internal reflection. Total internal reflection. All right, now let's see what happens if we change this index of refraction. Well, notice what happens. Okay, if I increase it, and now I make it so that it's a slower medium than the water, it bends towards the normal. But notice when I make it a faster medium than the water, it bends away from the normal. And let's make that difference even greater here. And so here you can see that effect even more. Glass is a much slower medium than air, and so it bends much more towards the normal. And then if I decrease that and eventually make it equal, right, there's no bending at all. But we can see the difference in bending depending on the index of refraction, which is what we already talked about in earlier slides. Now, another thing that's interesting to look at here is the prism. And let's take a look at this prism here. And we're going to shine white light into it. Turn it on. Okay, so if you look at what the prism's doing, it's kind of like the opening image. The prism is spreading that white light into its constituent colors. And the prism does that because different frequencies of light refract a little bit differently. So the higher energy frequencies of light, like blue, are going to refract a little more, bend a little more, and then the lower energy frequencies will bend a little less. All right, we're actually going to come back to this animation in a second when I talk about rainbows. But first, let's continue talking about total internal reflection. So total internal reflection happens when the incident angle is equal to the critical angle, or greater than. Or greater than the critical angle. Total internal reflection occurs in binoculars, optical fibers, and diamonds. Let's look at each one of those. So let's take a look at the binoculars. What we have is the light comes in, and then it refracts through a prism, but double refracts through it, and then comes through into the other prism, has total internal reflection there, and then goes to the eyepiece. Okay, so it's kind of it's a handy way to redirect light. Total internal reflection is, and that's one thing it's used for, a handy way to redirect light. In optical fibers, which are this is used in communications when you're carrying data with light beams, and optical fibers can carry a lot more data than regular wires can, than electrical wires can. And the way they work is they use total internal reflection to keep the light just bouncing around in the tube. And so this tube could go for miles and miles and miles. The most spectacular example, I think, of total internal reflection is the diamond. So the diamond has a very high index of refraction. It's about 2.4, and that means that light is traveling almost half its speed within the diamond. And so what happens is that although some light will leak out of the diamond, as light always leaks out of transparent things, well, there's also light that gets trapped in there. And it might get trapped in there, bounce around a few times, and then exit. But this is what causes diamonds to look like they're sparkling, because there's actually light at every moment. There's some light just trapped inside the diamond, bouncing around with total internal reflections before it finally reaches a face that it can escape from. Now, refraction is, I think, one of its most beautiful effects is in the rainbow. And rainbows are all about refraction. So the index of refraction varies slightly with the frequency of light. So the higher the frequency, the higher the index of refraction. We talked about that already. For simplicity, we're just going to talk about blue and red here. In actuality, this would be, we'd have to talk about all the different colors of the rainbow, but we're only talking about blue and red here. All right, so if the white light enters the prism, well, the high energy blue is going to refract a little more than the lower energy red, and so we get a spreading there. And this means that the refracted light is spread out in a rainbow of colors, which is also known as dispersion. Okay, so refraction can also be known or called dispersion because we're spreading colors out. Now, rainbows are created by the dispersion of light as it refracts in a raindrop. Okay, so if white light enters a raindrop, it actually refracts on its way in. You can see that the light beams have diverged. And then those light beams bounce back, and so there is some reflection inside. Now, why is there reflection inside the droplet itself? Well, because it surpassed the critical angle, and because it surpassed the critical angle, the light, most of the light doesn't get out here; it just stays in. It stays in, and so what we have is this will bounce in here, and then it will exit the water droplet with the colors spread out. And notice that they're spread out at different angles. So in this particular raindrop, we have a 40-degree spread for the exiting violet light, and then a 42-degree spread for the exiting red light. All right, so as the drop falls, all the colors of the rainbow arrive at the eye. So let's right now remember we're only talking about blue and red, or violet and red. Okay, so notice that sunlight is hitting a droplet here. This is a single drop, and all along the path of this single drop, light is entering it and spreading out and refracting. All right, well, at this particular point, when that refracted light exits out of the raindrop, certainly all of the colors come out. But the angle is such that, or the angle between the drop and the viewer's eyes, is such that the viewer at this point is only going to see red. It's not until the drop has dropped a little bit more that the angle is 40 degrees, and at that point the viewer will see blue. And so the viewer will only see the colors that correspond to that angle. Now, at any one time, of course, there could be one droplet at 40 degrees, another droplet at 42 degrees, another droplet at 41 degrees, and all the different degrees, right? Because we're not just talking about one droplet, we're talking about many droplets. And so at any one time, there's going to be hundreds of droplets at the right angle to produce a given color. And this is exactly why we see rainbows. Here's a beautiful rainbow in Virginia. This was actually taken by Therese Bowles last year when she was visiting her grandma in Virginia. Beautiful rainbow there. She actually sent me the picture a couple months after taking the physics course, and as she looked at the rainbow, she remembered this phenomenon of dispersion. So you could say that physics changes the way you see your world. I've had other students tell me as well that they sometimes see lines of force or think about charge and capacitance when they see electrical phenomenon, and that's good. If it changes the way you look at the world, that's good. If it makes you think about the way things work, that's good. But most of all, what I hope is that physics will help you see the grandeur and beauty of the Creator in all of His awesome creation. Here is another shot of that same rainbow that Therese saw at her grandma's house. It's a really good shot there. You can see the spreading of colors. And keep in mind that the color that you see depends on the angle between the water droplet and your eyes. So of course, if someone else is observing the rainbow from a different spot, they're not going to see it in exactly the same way. This is also why a rainbow can move with you as you walk, because your angles are changing, and the different droplets that have the right angles or the correct angles to your eyes or your line of sight, those are changing. Now, sometimes a faint secondary arc can be seen, and the reason this happens is because there's a double refraction. All right, so look how we see the main rainbow here, and the order of colors from violet to red, Okay, so like on the right side, it's the violet side, left side is red side. Well, notice on the secondary one, it's the opposite. It's switched. Well, I'm going to kind of explain both why there's a double and why it's switched. Okay, so let's pretend now that we have, let's say we're looking at two raindrops here. All right, and let's make it white light. Okay, so notice what happens here. Okay, so pretend this is a raindrop, and light's refracting through it, spreading out into its colors. Well, what if we put another raindrop in the vicinity? Well, now notice what happens. Okay, so let's consider this our primary rainbow here. Notice that red is on top. But then when it refracts through again, red's on the bottom. So it's flipped. What's happened then is you have a double refraction. Some of the rays that exit one raindrop will now enter another raindrop and refract through it. And that's what produces the secondary colored arc. That's also what flips the colors of the colored arc.
The homework is Project Report 1 and study for the chapters 23 to 25 test that will be at the end of this week. See you in class.